show you movies at some point, but
You use the computer.
after, yes. I just show you movies.
You start on the
Yes,
blackboard.
yes.
Excellent.
The blackboard. I prefer.
According to this clock, it's still
Clock.
a moment. Well, this talk is by Evan Fau from Berlin on the analysis of splitting methods. Reaction diffusion? Right.
Yes, for reaction diffusion problems. Thank you. So the purpose of my talk is to analyze the splitting methods applied to reaction diffusion problems, and I would like to show you that using basic rules of stochastic calculus, you can show. You can reprove existing estimates, and you can also show new estimates concerning especially the nonlinear case. So I will essentially present a simple case. So I mean that the diffusion part will be only the Laplace operator, and I add to this operator a nonlinearity. And so this is for the time is positive and x. So the space variable belongs to some RD. Okay. And so there is a starting eigenvalue, starting values here, which is given. And the splitting method. So splitting is based on the. So here this is the heat propagator, and the flow of G, which is so the flow of this part, which is essentially an ordinary differential equation, and we call the flow phi, so satisfying this equation. Okay. And the splitting, so I will essentially consider three splittings. So this is reapproximated ut by, so the Lie splitting times phi, or the other ones, okay. And I will also consider the strength splitting. Okay. And so I will first give you a result, the following result. So we have the following approximation result. If you compute the difference between the exact flow of the reaction diffusion problem and, let's say, this one for the beginning in LP, so here in LP, then you have a convergence rate of order t to the 3/2 u0 in LP. So this is really, if you see the operator as an operator from LP to LP. If you want to have a local order 2, you here need to have a higher order of derivative. So I will give you two proofs of these results.
What is E?
Sorry?
Is this a fit there?
Sorry?
E, TV.
Okay. I should first consider, I'm sorry, the linear case. Okay. Now this is the problem with the blackboard, is that you forget the order. So I first consider the linear case. So in this linear case, so this means that g of u equals to the multiplication by a potential function, x of u. Okay. So in this case, phi of t of u, I write it as just e t plus t of. Okay. Okay. So the first is a deterministic proof. And I will give you, in the case of 2, and it's essentially based on results by Tobias Janke and Christian Lubich. But you can also find in many different papers same sort of results. And I saw, in fact, this proof, especially from L2 to L2. I saw it was in Lyon, and Marc Massot proved from L2 to L2. Okay, so the deterministic proof. So it's in the linear case. So you start with the Abel formula that states that this propagator can be written et delta plus an integral of t minus s delta times v is delta. And this is, there is an error here of the order t to the square times the norm of v to the square. And here, this is in the sense of operators from L2 to L2. Okay. And here, what we used to have this is that we use this, the heat propagator from L2 to L2 is bounded. That's all what we need here. And if you write the same thing for the splitting, so et v et delta, and you develop now this exponential, which is a function now of v, and so you get the same thing, delta, and here you have t times v times et delta, and plus. Okay. And so if you make the difference, so let's call R the remainder term R from t, which is the difference between the two, minus the splitting, can be seen to be the difference of two integrals. So it's an interpolation, it's a quadrature error, can be seen as the difference between some function f of s minus some function f of t ds. And here the function f of s is the integrand here. So, okay. Minus delta times v. Okay, well, you write this as whatever. Okay, this is equal. Okay, if you make the difference. So r from t is equal to the double integral of f prime of s ds. And if you compute f prime, this is equal to, so there is t minus r delta, and here there's a commutator between v and delta. Okay? So that you have to control the commutator of delta and the function v. And what you get is that if you compute r and t, the main contribution will be the difference. So it will be an operator of order 1. So I write it like this. So d is the derivative, and you will have e s delta as an operator from L2 to L2 times the sigma plus a remainder. Now if you compute this norm, this is less than the supremum in Fourier, for instance, of xi exponential minus sigma xi squared. Supremum from xi greater than 0. And if you can see by taking, for instance, xi of the order 1 over square root of sigma, that this is smaller than a constant over square root of sigma. So now, if you integrate this term, you get the t to the 3 half. That's the deterministic proof. Some remarks. So it was here given in the case p equals to 2. I don't know if you can prove the same thing for any p. Then you need regularity on v. Essentially here, you need v to be at least C2 and bounded. Okay? And what you also need is that you need that the heat kernel is regularizing. This is here. This is this argument. If you can't do this, then here you just have, it's not bounded operator. Okay? Okay, so now the probabilistic proof. So the probabilistic proof starts with the Feynman-Crack formula. So we are always in the linear case, okay? So here this is dtu. And the Feynman-Crack formula says that u at the time t at a given point x is equal to the expectation of u0 in x, big X t, little x, exponential of ds. Okay? And here x, this is a stochastic process. I mean, in this case, it is essentially a Brownian motion. So scaled by the factor of square root of 2. This is not starting in x. And this is an array. To prove this, it's just an Ito formula. And it's a sort of variation of constant formula in the stochastic case. Okay, so this is the exact solution. Now, if you write this for the splitting, so this is ETVX here, and you have now the heat propagator, and you write the Feynman-Crack formula for the heat propagator. So this is only this. Okay, this is ETV, ET delta, ETX. This is equal to this. And now if you make the difference, so if you look at the R from T, this is essentially the expectation of U0 on x dx multiplied by the exponential of t vx minus the exponential of integral of t v of x. And so you see again that it is only a quadrature error formula, but for a stochastic process. Okay. So now we just assume that V is bounded, that V is Lipschitz. This is only what we need. And you see that, so I write it in, I take the supremum in x, so I look at the L infinity norm. This is less than, so you have the U0 in L infinity. Then you have, so V is bounded, so use exponential. So you have some constant here depending on a T0, T0, so T more than T0. Here you have M. And then you have the Lipschitz constant of V, and after that you have the integral of, from 0 to t of the difference x minus x dx, expectation of. But this is only a Brownian motion, essentially. And so you can compute directly. I mean, this expectation here is exactly, strictly less square root of t, so that if you integrate it, then you get t to the 3 half. So this is a probabilistic proof. So so you see the difference is that here you can take V much more less regular, and you don't need the regularization property of the diffusion part. It means that it can extend to equation of this form. So you can have a divergence of matrix A, right, U plus x transpose quadrant of U plus V. But in this case, you have to consider a more complicated stochastic process. So in the case where A can be written as a product of matrix of this form, then you will consider something. So F, okay, it's a slightly modified vector field here. It depends on A2, but essentially it is. You will have to consider a more general stochastic process, but it will work exactly the same way. In this case, maybe you don't have the estimate for any p, but maybe only for L infinity. To have it for any p here, it's just because the Brownian motion and leaves the Lebesgue invariant. So it says something important.
What are the conditions for the Feynman-Kak formula?
Very, I mean, very.
Because you said you didn't need all the regularization as you in the analytic problem.
To show this, you mean?
No, yeah, what are the conditions for that?
Well, essentially very low conditions on the potential. You can define this in the case where V is Lipschitz. You can define this.
So the conditions are weak and the conditions.
Yeah. Okay, I will tell you.
Just one more quick question. How do you pick up this F tilde for your drift part in the
Okay. Well, in fact, you can write it. If you can write it this way, this is the Ito formula. And then here you have the square of U plus F plus V. Then it will be the stochastic process dx equals to f of dt plus sigma of dw. So this is just the modification between this formula and this formula. So essentially the term you will add is the derivative of A, or the divergence of A with respect to one column.
This term you will have also in linear case where G just VU, right? Because it's essentially a drift term. So I'm just trying to sort of to put analogy to this term in the original equation, and I sort of cannot see that.
You mean with the nonlinear
the
case?
equation that you're trying to solve.
Yeah.
There is no drift term there as such. So.
No, it's just you consider this equation and you consider the splitting method given by first you solve this and then you solve this.
Right.
Okay. So I will now talk about the nonlinear case. So in the nonlinear case, so you don't have the Feynman-Kak formula in general. I mean, you have a probabilistic representation of reaction diffusion equation, but they are quite complicated as far as I know. And but you don't need it. You only need the Ito formula and the Martinez property. So if you have a stochastic process satisfying this, so it's very general. So you can think of F as a vector field and sigma as a matrix. And this is and the Ito formula is just a stochastic chain rule. So if you have a big function depending on the time t and of a stochastic process x of t, then if you look at the differential, so you have the differentials with respect to the time here. Then you have the usual chain rule term. So here, and apply to this vector plus sigma. And then you have the last, the so-called Ito term, so which is equal to 1/2 the trace, so this is origin of the divergence of the Laplacian 2, of sigma transpose times the Hessian of f dt. So we only need this formula and the fact that for any function the expectation of the Ito integral of any function x dw, this is equal to this. It's the Martingale property of the Ito integral. That's all we need. Okay, so the nonlinear case. So in the nonlinear case, the trick is to, in fact, is you. So let's consider the splitting method Vt delta. Okay. Now you apply the Feynman-Clark formula to this splitting method. So you can write that this is the expectation of Vt in u0 in atx. Where here, this is only the same Brownian motion as before. Okay? And the idea is to consider the following process. U of s equals defined as phi of s applied to u, the exact solution of the original problem. You assume that you have existence, of course. It's just really for numerical purpose, so you are not concerned with the special study of this. So u of t minus s xs. Okay, so you consider this process. Because in u of 0, so s equals 0, this is identity. This is u of t and x. So this is the exact solution in x. And u in t, so this is phi of t, u in 0, but this is initial value, times x of tx. Okay? So that the error, so between the exact solution and the splitting method here is only the integral, the expectation of the integral from 0 to t of dus. So now what remains to be done is to expand dus and then to try to find which terms are the leading terms in the error. So I will give you now essentially the main arguments in a few minutes. So you want to compute the derivatives, so the differentiation of u of s. So you first have, so you want to use the Ito formula, you first have to try to find the differentiation of this, so the differential of this. So xs, so you use your Ito formula, so this minus the derivative with respect to the time here of u, so the exact solution, times dt. Then you have the normal chain rule term here in xs. And here you have dw and a scaling factor, okay, because dx is square root of 2 times dw. Okay, so. And you have the Ito term, and the Ito term is exactly the Laplacian of u. dt. So that when you replace here, because this is the exact solution of the problem, so it begins by minus Laplace plus g. So that the differential of this is equal to minus g of ut minus s xs dt plus square root. So now, okay, from now on, I will not write what is inside of this. It will be more easy. And you have the martingale term, du times dw. Okay? And now you compute dus. So first, you derive with respect to s. So this gives you g, because phi is the exact flow of the reaction term. So this is j of phi s of u. I don't write the argument again, times ds. Here it's not dt, it's ds. Then you have, so a first term, which is, so phi s prime, which is a derivative with the initial condition. Phi s prime in u, times, now you have this part. So this part is minus g of u ds. And you have also the martingale part, which is phi s prime of u times square root of 2 times dx of u, dw. And the Ito term is phi, the second derivative of phi of u, applied to, so sigma transpose here, but sigma transpose, so you have a factor 2 here that disappears in the Ito formula. This is the norm of the gradients, the norm, the Euclidean norm of the gradient vector of dx in u. Okay? Square. Now, this term disappears because it's just, it says that the transport by the This is a variation of constant formula. So transport of the vector field along a current line is equal to 0. So this term disappears. This term is a martingale term, so that the error is driven by this term. Okay, so you can write more precisely that the error here is equal to minus integral from 0 to t, the expectation of the second derivative of the flow of u. So here I write again t minus s xs times the gradient here. So this is the exact solution, okay? Okay, so now, for instance, you take the infinity norm, and here you use just the fact that the solution remains bounded. I mean, for along the solution. So, I mean, this term can be bounded by the gradient of u0, which is just in the L infinity. It's nothing. You don't ask much. Only that g is bounded and maybe it's derivatives or something like that. And so here, phi s double derivatives. This behave like s provided g is something like cv2, bounded to twice continuously derivable and with bounded derivative. So that at the end you find, so here you have s, you integrate it, so you have a t square, and here you have the gradient of u0 in L infinity square, which is sort of yes.
But just a second, you are considering non-linear case. You haven't made sort of any specific assumptions on the function g.
Of course.
And you are saying that solution is bounded. I mean, it's easy to construct an example of blow-up solution.
I agree.
So why are you saying that it should be bounded if you haven't made any assumptions?
I assume that g is bounded. I assume this to write down like things. Well, of course, there is always a tricky argument saying that if your solution is bounded, then g can be bounded, so something like that. If your numerical solution is bounded, you can always consider that g is bounded.
They are sort of...
No, but I mean, if you want to write down things for the numerical approximations, you sometimes have to do this sort of functions. No, this is not the point. I mean, the point is not to analyze the exact solution of this PDE. It's just more that if you are in a good situation, then how can you numerically approach this solution?
But numerically, I mean, again, numerically is a well-developed methodology also in stochastic light. If you put into correspondence to this equation a certain Markov chain, for example.
So I will okay. That's a very good question, because now, so I just give I will derive from this hybrid Monte Carlo method based on this approximation. So it's probably in the direction you want to go. So I just say what we have in the case of the strong splitting. So in the case of the strong splitting, you have, of course, you win something, but you lose also another. So here times u0 in L infinity. Then you can show here that it is of local order 5/2. And here you have essentially a constant that depends on higher derivatives, so non-linear that depend non-linearly of, well, so I write this. Okay.
What do you get if you make the strong splitting in there?
I don't know. I haven't. I don't know. Probably the same. I mean, they are conjugates. No. No.
No, I just asked this because the Stefan Pecon, for instance, written a paper where he states that you have to do it in the correct order.
That's true, yes. In fact, I was able to prove this. I started to try to prove the same thing for the others, because it was really ugly. So I said, okay, let's do this only for this. It's not the main important point in this. But maybe it has something to do with this. But it's more an asymptotic property in the work of Descamps de Meumeur. But yeah, okay. Okay, so now the next point of my talk. So this is. This is, maybe this is 3, I don't know if I can count it. So, a numerical algorithm. So, if you want, for instance, if you consider, for instance, the linear situation, well, the very standard probabilistic method to compute the solution is to use a finite formula to discretize it, and then to simulate your Brownian motion, and then to take the average at the end. So using a statistic central limit theorem, Berry-Essen inequality, etc. Here, so the idea is the following. So you have, let me describe the algorithm in the case of the real line. So you take a grid on the real line, which is J delta x, J belonging to Z. And you take numbers u, n, and j, which are approximation of u in the time n time h, and in the point xj. So here h is the step size. It is the time step. So the idea is to use the stochastic, the statistic representation of the splitting itself, and then to do the average, and then to continue the process. So first, you interpolate these numbers. So you build some u tilde n, which is an interpolation of the numbers u. You can use splines, finite elements, what you. Then you essentially find an approximation Vn, which is E of h delta times u tilde n. And you do this using the Monte Carlo simulation. So you build the numbers V and J, which are the average, 1 over m. M is the number of draws, sum from n equals 1 to big M, of u tilde n in the point of the stochastic process x at the time h, so you do m draws of this, and starting at the point xj. So in the more general case here of if it is not the Laplacian, you have to use an Euler numerical scheme to approximate the solution of this stochastic process. And then you do the splitting. Then you do splitting, which means un plus 1 j is equal to a numerical integrator Vh of un of V and J. Okay? So what does it do? What does it do? So if I try to draw, so here in the Monte Carlo situation, so in the standard Monte Carlo situation, here you have the time t. You start from a point x, you use your probabilistic representation, then you let your Brownian evolve, and when you are here, poof, you take the average to get a value of this. Here what you do, you start, so you have a grid, so you start here from point x, you let your Brownian motion evolve like this, but after a time h, then you take the average. And then you continue again. And then you average again, etc. Okay?
Sean? Would it be better to go backwards in time, actually?
Sorry?
Wouldn't it be better to go backwards, to do the trajectories backwards?
Backwards?
Well, I was just thinking, if you really have advection in there as well, I mean, if you have a drift term,
Uh-huh.
I think you would need to go backwards.
You mean with the difference between Fokker-Planck and Kolmogorov? That's what you mean? No?
Well, might be sort of the dual picture here. But I mean, it's so you would basically look for trajectories that end up at the grid point, starting at the lower level. So you would flip that picture around.
Yes, but in this case, you will solve the Fokker-Planck equations.
Yes.
Backward, which is it's essentially the same, isn't it?
Well, not if you include that. Not if you. I mean, for the Laplace, yes, but I mean not for the.
I agree.
If you have.
For the more general case, and if you, especially if you have non-linearity, that's what you.
No, if you have
advection.
yes, advection.
Yes, I agree. Yes, but so does that work? Yes. Okay. So this is a very simple example. This is in the linear case, where V is just so minus the harmonic potential, and U0 is exponential minus. This is a Gaussian. Okay. So you can compute the trajectory exactly. Okay, that doesn't work. Okay. So so movie. So the first number is the step size, so 10 minus 2. The number of draws in the hybrid for the hybrid algorithm, and for standard Monte Carlo algorithm, discretization of the Feynman-Clark formula. Then this is delta x, 10 to the minus 1, and 1 is the final time. So. Okay, well. So what you can show is that, so in green this is a Monte Carlo simulation. And in red this is the simulation with this algorithm. And you can see that it is much, much better in this case. So, and I think it's because, I will, maybe if I have time I will explain this a little bit, but it's because here you only have a process with very small variance. And this might explain the thing. There is a price to pay. So I would also like to show you a movie concerning the Burger's equation, because if you I think you can apply this to many situations, because you only have to discretize a local heat propagator, and you don't need to have a probabilistic representation of the global solution. And in particular, you can also have systems, which is impossible in the general case to have probabilistic representation of systems of reaction diffusion. So, so for the Burger's equation, so dTu plus this is equal to plus u. So assume that un so is an approximation of the exact solution. Then you consider, so it's a function, so here it will be essentially un tilde, an approximation of the function. Consider this equation, dtu n plus 1 plus un gradient of u, n plus 1, equals to the viscosity times un plus 1. Then, using again the Ito formula, then this is exactly, you can write it that the expectation of un in xt, where xt is a solution of minus un of xt dt plus this. Okay? And then you can discretize this. You can, exactly as before, you can use here so splines, functions, and here you use an Euler scheme for this. Then you compute this step by step, and so you get a scheme for the Burger's equation, though it is not exactly a reaction diffusion system. So so this is the result maybe. Well, so there is a movie, so I wanted to show you the movie. Maybe it doesn't work. So Burger's. Yeah, so this is with a small variance of this. Okay, this is with variance 1. And okay, so yeah, so in blue this is the exact solution, and in red this is the solution computed here. But here I probably have taken a delta x 10 to the minus 2 and h 10 to the minus 2, so it begins to be very good in sort of approximations. But I mean, you can have apparently consistent schemes for this. So I will end by just discussing a bit the error, a tentative, give you a tentative error estimate of this error analysis at least.
I see no shock in this movie.
You see no what?
Shock.
No shock. Shock. Okay, if you want to see shocks, well, this is the viscous burgers. Okay, so, and nu is equal to 1. If you really want to enter into these details, things are quite more complicated because you. Okay, this is something you can do. You solve this with an entropic scheme, and then you solve this part with this scheme. Could be another possibility. And in this case, it will be consistent with nu when you let nu tends to 0. If not, I don't know if you get the correct solution. I'm not quite an expert in these things, but I will be very cautious. Okay, so on the blackboard again. So I would like to try to give you a tentative error estimate for this. Okay, so you have 3 steps here. So if you look at the local error, so for the step 1, so this is an interpolation error. So you have a term called delta x to the p. P is the order of interpolation. So if you can use linear interpolation, you can use splines, you can also imagine to propagate the derivative and then to obtain higher order. Then the second step 2. So this is statistical error. So you can use so this is essentially a central limit theorem, but if you really want to write down things, you have to use Berry EC1 inequality, so which give in fact an asymptotic, and the Edgeworth asymptotic expansion. So that states that more or less the error between this Vn and this Vn is of the form, so the variance of the process over square root of m times a Gaussian here. And when I say that if you use this sort of things, you can write that this is plus. You can derive uniform estimates in particular. Okay. But here's the variance here. This is h, because this is a stochastic process. Okay? And the third error, so it's a splitting error. So here you have h to the power something. So if you use f to the 3 halves. Okay, so now if you look at the global error, so essentially it accumulates linearly like here. Of course you have, I don't want to give you here a proof because it's not written in fact, it's a tentative estimate really. So if you accumulate these terms, so the first one will give you, so n times h will be equal to the finite time t. So here you will have n times delta t, delta xp, so this is of order, for big T fixed, this is delta t, delta xp over h, which is solved by news. And you see that you have an anti-CFO condition. But you can control here this term. You can really work on this to try to find better approximation, better spatial approximation to deal with. The second behaves like this. You make the sum from n equal to 0 to n. So this is really more difficult if you want to write down the things. But essentially it's like this. You have to use more refined version of the central limit theorem. But it is really the philosophy. You make the sum of Gaussian process. And this behaves like h over square root of m times the square root of n. But n is t over h. So this behaves like the square root of h over the square root of m. And here you win. Because in the standard Monte Carlo case, you have here a t over square root of m, whatever you use to discretize your stochastic process. And the third case, it gives you a global error of this form. Okay? So these are the 3 leading terms in the error. While if you use the standard Monte Carlo method, then I think that work of Thalet and Tubarro for the weak in fact essentially weak order. There is an error of the form T, or square root of M plus H. Okay, so now we try to discuss what is the best, etc. Okay, I will stop here. Thank you very much for your attention.
So thank you for your interesting talk. Other questions?
Coming back to your burger simulation, so isn't that what you're doing? I mean, you have these sort of stochastic paths that you shoot out, but they essentially Gaussian distributed, right? More or less. So why don't you just average with a Gaussian all the interpolated values?
You mean when you reconstruct the function?
Yeah, when you do this propagation step, right? So it's basically as a drift term, that's the velocity. You freeze it over one time step, right?
Yeah.
So that gives you a drift, and then you have, on top of this, you have the diffusion process. So there are these spreading out trajectories. But they, because it's a small time step, is more or less Gaussian distributed, right?
Yeah, but it's a small variance.
Probability.
The
Yeah, with small. But why don't you just use a Gaussian to do the integration? I mean, why do you shoot out these things to do integrating a function over a Gaussian distribution? It seems just a complicated way of doing this integral, right?
I don't understand what you mean. I understand your point.
Well, the distribution of
Yeah.
the probability that you find a trajectory around this mean path, which is given by them, is Gaussian distributed.
Yes.
It's a bell-shaped curve, right? Now you sample from that distribution essentially.
Okay.
Right? And then you take the sum, which is essentially an approximation of the integral of that.
Yeah, in the case where the viscosity is constant, okay.
Yeah, right.
If not, in more general case.
Yeah. But
Okay,
I mean, in
why
this
not?
case, I mean, it's mentally it is sort
Mentally.
of, is you transport the current value of your field, but on top of this you take a local average, and that is actually where the viscosity naturally comes in. I mean, also that where the shocks get smoothed out because you take local and average.
Yeah, this is a fine formula for the scheme and road.
Right.
That you have now which over the Gaussian. If you write a kernel.
Well, it's essentially, yeah. If you have an approximation with that kernel, then it seems much easier.
Then it's the same. I mean, what just, in fact, maybe the more general philosophy is that if you have a local probabilistic representation, so here it was something like this, where actually this was a Gaussian. So you can write it perfectly as an integral of something, okay? But my only point is that you do you find an approximation from this, and then you go again from the beginning. You don't follow the stochastic process, because then you have variance.
Yeah, then it's lost, and then you can't do this anymore, right?
Yeah. And also, so you can have the same thing for high dimension, for systems, from Navier-Stokes equation, or for whatever.
Yeah, I sort of would like to come back to what I asked you when you moved to this numerical algorithm. I mean, basically, sort of you're moving with these small steps, right? So from this previous time step to the next, you have to hit this next time layer. So basically, the probability that you would hit this time layer will sum up to 1 for each time step layer, right? And that's basically the methodology that is used, for a long time in the Markov chain approximation approach, which basically you do the same. You have your deterministic equation. You put into correspondence to this deterministic equation a certain stochastic process, and then you discretize that. And that's exactly what you're doing. So question is, so what basically the difference between this, I mean, there are many textbooks on that.
Yeah, but
Kushner-Dupuy is one of those.
I don't know.
And again, if you take that book, as far as I remember, you also could find even Burgers equation example there.
Yeah, but you have probabilistic representation of the Burgers equation.
Right. So can you explain sort of what basically the difference between standard Markov chain approximation approach to PDEs and what you are proposing here? I appreciate completely that you sort of are doing quite interesting things related to these estimates and you're trying to sort of preserve that. But in terms of the algorithmic development, that's essentially what I'm asking.
That's what I explained with the two different cartoons, so with a small.
Right, but
And if you propagate the, because if
Right,
you do the standard Monte Carlo approximation, I agree that you have to simulate your stochastic motion, your stochastic process from 0 to t. But then you follow a trajectory,
yeah.
which has a big variance.
Yes, but I'm not talking about Monte Carlo. That's
Uh-huh.
I'm talking about the Markov chain approximation approach, which is certainly not Monte Carlo style
Okay, maybe.
approximation. It basically works exactly in the same way like you are sort of describing. And actually, in addition to that, what you could show that many approximations that you construct on the basis of the Markov chain approximation approach would coincide with pretty well-known numerical schemes.
Yeah, but
and it's exactly what you could do, for example, with Brooker's equation.
I would be glad to see.
Well, as I said, it's sort of well documented and there are textbooks on that. One of them is Kushner Dupuy.
So when I did this, so I mean in INRIA, so in INRIA we have Denis Tallet, so I wrote him to have his mind. So apparently it's Arnaud de Buche. I mean that's okay. I'm not a probabilist, so I'm not really used with all the techniques. But so
Maybe
when
this
you
technique is more general, but that's exactly what I'm trying sort of to understand.
I mean they didn't answer me. Well, it's well known. That's just my point. Now, if you have, I'm sure that, for instance, people in fluid mechanics, they probably at some points do something like this because it's quite natural. You simulate, and then you average, and then you simulate. It's natural. But I read. But, I'm not seeing the same thing exactly.
So do you preserve the L1 norm of U?
Do I presume?
I mean, is it a conservative scheme?
Oh, that's a good question. Well, everything, I mean, does this preserve the L1 norm? I mean, this plus the interpolation.
Yeah, well, right. That's where it gets fussy, right?
Yeah. I don't know.
But that's essential to get the shocks right. That's probably worthwhile checking.
Well, when you take a small viscosity, the good news is that here you already have this small viscosity here. And you will also have this small viscosity here. Probabilistic methods are good for small viscosities, probably.
Oh yeah, that's definitely.
So the problem is to recover the shock correctly. So to converge towards the entropic solution. And this is not. It's not clear.
Further question? Seems to be the case, so thank you again.
Thank you.
Yeah, I mean, I guess what you can think maybe is for Burger's equation, try to really write it as a finite volume method.